there's not much of the traffic. The cars are moving really fast, and this one is really slow. There's a traffic jam. You know what's going to happen? We have a lot of cars in Albany, right? There's a lot of accumulation of the cars there. Right? And that's a one case scenario. How do I represent that? KA is much bigger than KB. Right? And what that means is A is converted to the I very fast, and then this conversion is relatively slow compared to the intermediate production. And if you do that, you will see this. You will see the significant rise, and then eventually it's going to come down. I mean, you will lose it at any rate, and this one has a finite concentration in the beginning, right? So you're going to lose it. So this is a concentration of an A. This is a concentration of the intermediate. Right? And then what happened was you will have the product, and their concentration is going to go up. This is your product. That's the, because eventually all the their destination is the product, right? New York City. So you will have all the car. Let's say you have 1,000 cars here. You have 1,000 cars at the end, right? So that's the scenario. But how many cars are stuck in the middle? And do I see something like that? And that's the sort of the graph that you can see. And depending on how big the difference are, intermediate can have something looks like that, or even something smaller. So they can have this. But one thing that is clear is, and this is seems to be trivial, but this A concentration goes to 0. Intermediate, you have nothing, and P goes to A0. And your answer that whatever you solve it should be like this. Okay? That's the one. Okay? So this is, if your product is something that you're intermediate, you have to time it right just to stop the reaction and then get maximum of the product that you want to get. Okay? There is another case. I'm going to draw the same thing. This is a concentration of anything divided by initial concentration. Same thing. This one goes down. But this time, I want to say A is much smaller than B. Okay? So then it means from the Montreal, very slow, a lot of traffic to Albany. And from Albany, there's like 10-lane superhighway to the New York City. Right? So what do you see? The moment that cars arrive, they're on a jet plane and shoot to New York City, right? So this is what that means, is KB is much bigger, much faster. Do you think that, what will be the concentration of, this is an A, what will be the concentration of I?
It's a really small home.
That's it. Okay, it does have a value, so there is a small thing, but it is like that. You see. Okay, and what's the product? If this is a case, actually you only see is an A happening into a P. And we have a very trace amount of I happening in a very small portion. So this is a case where you have a flipped second stage reaction is much faster than first stage, whereas this one is first stage, so there's enough congestion. This is congestion. Because the second step is a rate determining step, so this is a. And if you, like I said, if you solve this question by putting it in using the integrating factors, you will get this answer for what is known as I. And using that, you plug it in, you can solve it for P, and you will get the answer. And you will get the exact mathematical formula for doing this. And trust me, people do not like to do that, right? And so they want to say, is there any way that I can do a simple solution without solving this thing? Okay? These days, you guys put it in a MATLAB and they can solve it for you. In old days, and still, the way that you guys can do is, you should develop certain insight how do the back of envelope calculation. And this is some first one is coming from what is called the steady state approximation. Okay. Here we go. So state approximation is nothing but, I'm just saying this is steady state. So this is a steady state approximation is your intermediate concentration changes is 0. That's a steady state approximation. Then all of a sudden the life is easy. Okay? What that means is here, you know the y di dt is close to 0. What's that means? I'm going to write this is di dt. What's that mean? You have almost no changes of intermediate concentration, right? That's what that means, right? Intermediate concentration stays kind of constant. There are two scenarios. Here, this is where your di dt is 0, right? At this position. Other than that, this is not steady state, I guess. Everything is non-zero value except for this formula, right? So this case scenario is not good for steady state approximation. This case scenario, if you look at that, this is pretty much steady. I mean, it approximates, right? Close to 0. Right? So therefore, throughout, with the exception of here, any time, I think it's about 0. Once you do that, you are in business. I want to know this, right? You know what? It's just this. So from here, steady state approximation, I can easily write I is nothing but KB KA times A. Wow. Right? And then what's my A? We already know. So we got AB, AA, A naught, e to the minus AAT. Well, this is, you got this information right away. Okay, using that, I can plug that in, and I can solve this P as a function of time. To get this, how steep the rise is, to get this information. So the steady state approximation, applying here as an example. So steady state approximation is essentially trying to find something that intermediate, okay? And for here, remember, I guess I'm pulling it up, H2, BR2, goes 2HBr, which is very complex reaction. And then among this, and I'm pretty sure they develop hydrogen radical, bromine radical. There's a lot of reactions there. And this one is a sort of considered to be an intermediate, right? And your steady state approximation is the concentration of this is concentration of intermediate changes is. You put that in as a constraint, and then you can easily solve this equation in a couple of pages. And that's your PhD thesis. Okay, so this is what people do it in the 60s and 70s. With the computers, no, you can't get PhD for that. You need to do something more elaborate calculations. So to me, the steady state approximation happened this way.